You know that feeling when you crack open a hand warmer or an instant cold pack that just gets icy in a split second? It feels like that heat or that cold just comes from nowhere, right? Like a little bit of magic? Well, today we're gonna pull back the curtain on the chemical reactions that power all of that, from a self-heating can of coffee all the way to the glow of a firefly. Okay, so take a look at this. You've got a self-heating can, you've got a firefly. They seem totally different, but they're both asking us the same exact question. Where is that energy, that heat, or in the firefly's case, that light, where is it actually coming from? It really does feel like it's being created out of thin air, but it's not. The real secret isn't about creating energy. It's about releasing energy that was already there. And how that works is all down to one of the biggest rules in the entire universe. So, first up, the first rule of energy. And honestly, the subtitle here says it all. It's all about balance. You've probably heard that you can't create or destroy matter, right? Well, the same thing goes for energy. It can't just pop into existence or vanish into nothing. And understanding that one idea, well, that's the key to unlocking this whole mystery. And here it is, the big one, the law of conservation of energy. It sounds simple, but it is so powerful. The heat you feel from a hand warmer isn't being made on the spot. It was already there, just stored away as chemical energy. All the reaction does is transform it, changing it from one form to another. You can think of it like an energy transaction. Okay, so if it's an energy transaction, where exactly is the bank? Where is all this happening? It all comes down to the tiny little connections between atoms. We call them chemical bonds. And really, every single chemical reaction in the universe is just a story about old bonds breaking apart and new bonds snapping together. Now, this is the most important part to get. It's really two sides of the same coin. First, you have to put energy in to break bonds. Think about it like trying to snap a twig. It takes some effort, right? But, and this is the cool part, when new, stronger bonds form, energy gets released. So just remember this, it costs energy to break things, but you get a payout of energy when you make things. So whether something feels hot or cold, it's just the final result of all that energy bookkeeping. You just have to ask, did we get more energy out than we had to put in? If the answer is yes, it gets hot. But what if it took more energy to break the old bonds than we got back from making the new ones? Well, then it gets cold. It's really that simple. Now, let's see what that looks like in the real world. Which brings us to section 3, exothermic reactions. This is all about releasing heat. And the name gives it away, right? Exo means out and thermic means heat. So literally, heat out. These are the reactions that make things feel warm. And our source material shows a really simple way to see this happen. You basically just take some hydrochloric acid, check the temperature, drop a little piece of magnesium ribbon in there, and see what happens. Super straightforward, but the result is pretty dramatic. And yup, the result is crystal clear. The final temperature is higher than the starting temperature. The mixture got warmer. It literally released its stored energy as heat into the cup and into the air. This energy diagram shows us exactly why that happened. See, the reactants, the stuff we started with, are at a certain energy level. Then it takes a little bit of energy to kick things off. That's the little hump you see. But then, look what happens. As the new bonds form in the products, a whole bunch of energy is released, and they end up way down at a lower, more stable energy level. That huge drop is the heat that we feel. And this isn't just something that happens in a lab. This is exactly how those self-heating cans of soup work. It's how the thermite reaction gets so insanely hot it can actually weld steel railway tracks together. And, yep, it's even how a firefly makes its own light, just converting chemical energy into light energy. All right, so making heat is one thing, but what about the total opposite? That brings us to our next section, endothermic reactions, the big chill. If exo meant out, then endo means in. These reactions don't give off heat. They actually pull heat in from their surroundings, which makes everything around them feel incredibly cold. And the experiment for this one is even more amazing. You just put a beaker on a little puddle of water on a block of wood, then you mix 2 white powders inside the beaker and give it a good stir. You watch the temperature on a thermometer just plummet. And then you try to do the last step. Just try to lift the beaker.
And get this, you can't. It's stuck solid to the wood. That chemical reaction inside absorbed so much heat so fast from everything around it, including the beaker, the wood, and that puddle of water, that the water instantly froze into ice, gluing the beaker right to the board. How cool is that?
Now, if you look at the energy diagram for this, it's basically a mirror image of the last one. The reactants start out at a pretty low energy level, but it takes a ton of energy to break their bonds. That's that huge hill you have to climb. And the energy you get back when the new bonds form, well, it's just not enough to pay back that energy debt. So the products end up at a much higher energy level, and all that extra energy had to be pulled in from the surroundings as heat.
So that brings us to our wrap-up, nature's energy balance sheet. Because when you get right down to it, exothermic and endothermic reactions aren't really opposites. They're just two possible outcomes of the exact same process, breaking and making chemical bonds. Two sides of the very same coin.
And when you look at them side by side like this, it just clicks, doesn't it? Exothermic on the left, energy goes down, so heat comes out. Endothermic on the right, energy goes up, so heat has to go in. It all just depends on whether the reaction finishes with an energy surplus or an energy deficit. This table just nails it down for us. For exothermic reactions, thermal energy gets released, which makes the surroundings hotter. Why? Because the energy you got from making new bonds was greater than what you spent breaking the old ones. And for endothermic reactions, it's the complete opposite. Energy is absorbed, surroundings get colder, all because breaking those old bonds cost way more energy than you got back. And that brings us back to the big idea. It's not magic. That self-heating can, that instant cold pack, they're not creating or destroying anything. It's just smart chemistry. It's a reaction designed to either release its stored energy as heat or to absorb heat from the world around it to create new, higher energy bonds. It's a perfect energy balance sheet, all following that one simple law.
So now you're in on the secret. And once you see it, you start to see it everywhere. Frying an egg in a pan, lighting a match, even your own body digesting food. It's all just this same cosmic dance of breaking and making bonds. The only question left is, where are you going to see it at work next?